For the user interface, on the help support button, there are two buttons. The first one for profile button. This button, you will define here your information like name, phone number, and your email. Those information will be used during if you would like to make a report or send an issue to the technical team. The information will be included here in the report bug form. So from here we can send a reply to you by using the contact email. So the email you will define it here should be a correct email to send back the reply in your correct email. For the skins tab, you will find a huge number of skins. You can select the suitable one for you. And for the guide tab, you will find here some tutorial tabs and some standard templates. So let's check that with SEG software. Here for the profile tab, if you open it, you will define your information here. Okay, and for the tutorial tab or the guide tab, when you click on tutorial, you will get this form. When you make a refresh here, SEG will open the tutorial videos from the YouTube channel, and you should be connected to the internet, and directly from here you can watch the video or the training video directly from here. And from this button, which is YouTube, you will be able to open directly the YouTube channel on your browser, so you can watch the videos directly on the browser. The templates, when you click on templates, you will get this form. This form includes some pre-built projects for tanks, vessels, spherical tanks, heat exchangers, double-jacketed vessel ducts. So you can select the project from here, from get this template, and you can copy it in a path on your machine. After that, you can open it and study the tree of this part, how it's created, and you can generate the 3D model of this element by using some of the pre-built projects here. Now let's check the available modules in SEG software. Here, if you would like to generate a new project, you will get this form. As you can see, you will find different types of modules. The first type, which is the overall type, this type will give you the ability to create all features in SEG, like the features of ducts, feature of storage tanks, feature of spherical tanks, feature of heat exchanger, and piping and pressure vessel. So, for example, if you select a horizontal or vertical pressure vessel, you will not be able to create a tube sheet, which included in heat exchanger. The same for expansion joint; it will not be included on horizontal or vertical pressure vessel. The same here, if you would like to add a roof or a bottom or annular plates, it will not be included on a pressure vessel module. The same for ducts and spherical tanks. As mentioned, the overall module will give you the access for all features for all modules. For the project data, you can define the project information like project name, project number. When you select the project node from the tree, you will be able to make an access for the project information, and you can modify the information and save the information that you have. The equipment design data, you can modify the equipment design data and we will discuss that during the session of today, inshallah. And when you select the visual node from the tree, you will be able to define the design data of this equipment, like the construction code, internal design pressure, internal design temperature, and more. Okay, here for the modifying the equipment setting. When you select the equipment from the tree, after that open the setting tab, and from visual setting, you will get this form. This form will give you the ability to modify the visual setting. Here we have some different groups. The first one, which is changing the position of the equipment. So if you would like to make your equipment in a horizontal position, so from this drop-down list, you can select between 3 different options: horizontal visual, sloped visual, which is tilted visual with an angle from the horizontal level, a vertical visual. In the horizontal visual, you have 2 options to assemble your model. You can start from left to right, or start your assembly from right to left. So the reference point will be located on the first one from on the left side, and in the second one it will be located on the right side. Okay, here for the tilted visual, it's the same of the horizontal, but it will take an inclination angle from the horizontal level. So the same direction of the assembly, you can start it from left to right or right to left. The third case, which is vertical visual, you can change the position of the visual to a vertical position, like in a vertical storage tanks or vertical visuals or columns. So you can select the position from as a vertical visual. The direction assembly, you can modify it to start from top to bottom or bottom to top. Another group here for give you the ability to control the data entry for units. Here, if you would like to import the dimensions in millimeter or in inches, and select the precision of data entry, so you can change the data entry units from here. Visual service and the serial number, the detail of the equipment. You can change the service of the equipment, the tag number of the equipment, which is the visual name, and the serial number of this equipment. Another field here for the delivered blade dimensions, so you can change the length and width of the blade. And we will discuss this option in detail during the session, inshallah. For the main elements, you will have the ability to add the main elements to your model, like adding heads, shells, cones, flanges, covers, flanges, tube sheets, another items like expansion joints, Y joint for the skirt valves, annular plates, roof types, and duct types. Inside each type of those, you will find a different subtypes. Like in the head, you will find more than 17 types of head, like ellipsoidal head, hemispherical head, ellipsoidal head with crown and the knuckle radius, flat head, conical head. So inside this main type, which is head, you will find other subtypes. The same for the shell and other types. After creating one of those main elements, like head, when you select this element from the tree, you will be able to add attachments to this main element. Like when you select the tree, you can add supports to this tree, like a skirt or support pipe, support beam. You have the ability to add nozzle openings, like nozzle with external projection, nozzle with internal and external projection, weld OLED nozzles, couplings connected as a nozzle, and stud outlet. The ability to add internal attachments like impingement plates, vortex breakers, front pass partitions, clads, and external attachments like insulation clips, external rebads, and insulation. You have the ability to add different types of lifting lugs. Here, if you select the shell, for example, you will be able to add different types, like for supports, for example, the supports group. Inside the supports group, you will find the ability to add a saddle, stacked saddle, legs, lugs, and tilted saddle, skirt, anchor chair, different type of cradles. For nozzles, you will find different types of openings, and here you will find a clean outdoor, for example, nozzles according to the API with internal and external projection. For the lifting lugs, you will find different types of lifting lugs. You can connect it to shell and trunnions. External attachments like nameplates, external rebands, stiffening rings, nozzle ribs, insulation ribs, and many different types. It's the same for the internal attachment. You can add different attachments to this part. Here, let's start with the concepts in SEG, like the concept of the orientation. The orientation direction, how we can define it in Autodesk Inventor. Here for the horizontal vessels, let's start with the horizontal vessels. If you take a look from the back view, like that, you will find the view cube will appear here at the top right hand side. The orientation arrangement will start at the top at 0 degree, and the 90 degree will be on the right hand side. So the direction of the orientation will be on the clockwise direction. The 0 start at the top and 90 degree will be on the right hand side. For vertical vessels, the orientation will be like that. When you take a look and flip the top view to be like that, and the text in a flipped position like that, the orientation will be start at the top. So the 0 will be at the top here, and 90 degree will be on the right hand side, and the orientation will goes clockwise on that direction. Okay, another concept which is the for the main elements, how to make an assembly in SEG by using the start and end UCS. Here we have a concept in SEG, which is user coordinate system. In each element, we have a start UCS and end UCS. This UCS gives the ability to SEG to make an assembly. For example, if you have a body flange like this, after that you have another element like this shell. So to assemble this element with the previous element, SEG will collect the end user coordinate system here with the start user coordinate system for the next element. So that's the concept of the assembly. That's in case if you have start your assembly from left to right. The same for if you start from right to left. So that will be the start point, and here that will be the end point. So SEG will start collecting items by using this concept, the end of the first element with the start of the next element. The concept of datum. When you have an attachment connected to a main element like this nozzle connected to this shell, the location of this nozzle will be defined from the start point of this element, not another datum line like tan line or body flange, because this element actually located on this shell. So you will need to define the location of this one from the start point from here. So the datum concept in SEG different from the BV Elite, for example, or Compress. So you should define the location of the child item to the start point of the main element. Here a concept of gap, overlap, flip, and shift. This concept here in SEG software very important, because sometimes you may need to make a gap between main elements or make overlap between elements. Like here, when we discuss that for here, when you make a part on SEG tree like this shell, directly the end of this body flange will be connected to the start of the next element. But sometimes here you may need, for this cone, for example, you may need to connect this cone not to the end of the shell. Sometimes you may need to get it back a little bit in some cases. So you will need to make an overlap here. So the concept of gap and overlap give you the ability to make that. Now let's make a new project. Discuss this point here. If you create a new project, and from the new project tab, you will find the modules here. If you try to select one of those, you will not be able to select unless you define a name and location for the project. So let's create a project called Gap. From here, select the desktop location. Now you will be able to select the project module. From here, let's select overall and click finish to create the project. Okay, here after clicking finish, SEG will start creating the project file. Here we have this folder, which is called Gap, and you configure that you will have an SEG extension file. This file includes the project information, and it will take the same folder name, and this point is very important, and we will discuss it during this session, which is you will find the name of the project called Gap, the same of the folder, the same name, and the IBJ folder, which is the project file, okay, which Autodesk Inventor will read it to define the location of the project. So it will take the same name. And you will find here a folder for the assemblies, another folder for drawings, another folder for parts. So SEG will create all assemblies inside this folder, all parts inside this folder, all drawings inside this folder. So that's the construction of the project folder in SEG. You will find SEG file. It will take the same name of the folder, another file for the Autodesk Inventor project file, and it takes the same name of the project file. And here you will find three folders, one of them for assemblies, another for drawings, another for parts. And the old versions here, it's for a backup file. It looks like the backup file of the auto. Okay, now let's come back to SEG again, and here you will find the interface of the application. For example, let's discuss the setting tab. In the setting tab, this is the skins. Here, if you open the skins, you will be able to change the skin of the application like that. You can make it, change it by that way, make it pink like that, or make it with the like the Visual Studio interface. So that's the way to change the skin of the application. And on the right hand side, you will find the toolbox. And this toolbox, by drag and move, you can locate it on another location, like adding it here, for example. So you can move this toolbar on the left hand side, and you can figure that you can add elements like main elements like head, shell, nozzles, other attachments, API elements like that. So this toolbar gives you the same access for elements like element tab. So let's move it, drag and move, and locate it on the right hand side. Or let's close it. To open it again from File tab, you can show the tools by clicking on Tools tab. You will get again this toolbar. Let's set it back and close it. For the tree view, the same thing, you can move it by drag and move, and you can locate it on the location that you would like to locate it by dragging this tab from the top and move it to the side that you would like to make it appear. If you close this tab, for example, if you would like to show it again from show tree view, it will appear again. So by using show tree view, you can make this toolbar appear again. Now let's discuss the project information. Here for the project information, you can define the project information as we discussed, like project number, manufacturer, all of that. And for the design data, we will discuss it during the sample, inshallah. Now we would like to discuss the gap, overlap, flip, and shift orders. Here, if we have a head, for example, left head. Okay. And by selecting this head, if you create an ellipsoidal head, for example, make the inside diameter, keep all information as it is. Now, if you add a shell, which is shell 1, and select the shell type from here, define the length as 1 meter, for example, and click Save. Now, if you go to the Assembly tab and click on Start Assembly, here SEG will start creating, sketching the item and create the 3D model of this item, and you will get the assembly by that way. The shell directly connected to the head, so no gaps here. And if you take a look to the tree, here for the head, for example, you will find the end UCS will appear here at the end of the head. And if you take a look to the shell, you will find the start UCS here connected directly to the end UCS of the shell. And you will find here an end UCS at the end of the shell. So that's the concept of the assembly. Now, if you would like to make a gap between head and shell, how you can do that? Okay, now let's add a gap element. So from the elements tab, when you select the visual, you will be able to add main elements. One of them is a gap. So if you click on gap, let's add gap 1. And from this gap, you can define, as you can see on this image on the right-hand side, this element is not a real element. You can use it to make a spacing between main items. So let's make a space here with 100 millimeters and save it. Now, as you can see, the location of this gap comes after the shell, but we need it between the left head and shell. So how to move this gap between head and shell? So now we will learn how to make a move for a part on the tree. By selecting this node from the tree and right click, you will get this shortcut menu. And from here, you will find a move order. So you can move this gap after or before an element. So if you select after, for example, so that means you will make it after head, or before. When you select before, you will select the shell. So it should be before the shell or after the head. So let's select after, for example. So from here, it will be after the head. So let's click on move. Now, as you can see, the tree arrangement will change. You will have a left head. After that, you have a gap between head and shell. After that, shell. Now, if you click on Start Assembly, you can figure that you have now a gap between the shell and head with the same spacing that you defined, which is 100 millimeters. So from Inspect tab, you will open the Measure tool. Now, if you would like to measure the distance between this surface and that surface, you will find the value is 100 millimeter, and it will appear here. It's 100 millimeter, which is the gap that you defined. Now let's make another element, which is cone. So from here, let's select cone. Okay. And let's define the cone inside the diameter, the same with the outside diameter of this shell. So if you selected the shell, the inside diameter will be 1016, and the thickness is 10 millimeters. So the twice thickness plus this inside diameter should be the inside diameter of this cone. So from here, let's make it 1036. And that's the inside diameter, and the end diameter of this one, let's make it 1 meter and a half. Okay, the thickness of cone, let's make it 10 millimeters, and the longitudinal welding line orientation, let's change it, and the length of this cone, let's make it 1 meter, and click on save. Now if you click on start assembly, as mentioned, the created part will be connected directly to the end of the shell. Here, if we check that again, here for the shell, that's the start, the end UCS at the shell. Okay, so that's the end UCS at the shell. Yeah. And if you open the cone and select the start UCS, you will find that they are collected here at this point. So both UCSs will be located over each other here at this point. So if you would like to make an overlap, if we pick a section here, half section, and from origin planes, let's select the mid plane to make a cut here. And you would like to make this cone little bit comes to the back to the midpoint of this shell. So how to make it back and move the UCS point back here? Let's collapse this and come back again to SEG. And now let's add another gap option. So select the vessel, and from the element tab you will get a gap, and name it as overlap 1. Click enter. Now you have another point here, but this time let's select it as overlap and define the overlap value as 500 millimeters. And you take a look to the image on the right hand side, it will inform you that this item is not a real item, and you can use it to make overlap between elements. So here, let's save this one. And when if you select start assembly, you can figure that the arrangement of this node comes after the cone. Okay, but actually you will need it between the shell and the cone. So the same thing, we will do it by selecting this node, and from move, you can select move after or move before. The first time we select move after, let's check move before. So from move before, that means you will need to make it before the cone. So let's select the cone from here. So we will move the overlap before the cone. So move. Now, as you can see, this overlap point moved before the cone. Now let's click on start to create the overlap. Now you can figure that this overlap change the location of the UCS. So the end UCS of this point comes here. So the next point, which is cone, starts from that end point. Okay, so here by using this concept, you can make gap and overlap. Now let's make another option, which is flip option, which you can use it to flip the direction of the element, make it goes from left to right direction to another side, which is right to left direction. For example, here, if we add a pipe, for example, like pipe 1, and this pipe, let's make it as 24 inches pipe. Keep those information, just change the schedule, make the length of this one as 500 millimeter, for example, and click, let's make it 1 meter, and click on save. Now if you click on start assembly, the pipe will comes after the cone. So because the assembly direction start from left direction to the right direction. We take a print screen here and comes here. So the direction assembly start from that direction to that direction. Okay. So now if you would like to make this element only, which is this shell, what goes in that direction? You need to flip the direction of this element and make it goes on the other direction. Start from here, but goes in that direction. To make that, you will need to use the flip order. At this point, you will flip the direction of the assembly. Let's check that. Here, let's add a new element. So from here, from Elements tab, after selecting the visual node, let's select a gap option and make flip point, flip one. For this flip point, we will select the flip type and click on save. Okay, so by making a flip and move this flip between the cone and the pipe, because at this point you need to flip the direction, so it could be before the pipe. So from here, let's make it move before pipe one. Okay, and let's start the assembly. As you can see here, after the modifications, the direction of the pipe will be flipped. Here, if you take a look now, if you rotate it 190 degrees, sorry, the selected item here, let's select this one and let's rotate it 190 degree. It will be located like that. So you flip the direction of the assembly of at this part, at this point. Here we defined this point, okay, to flip the direction of the assembly. Now, any element you will add it before the pipe, it will goes in that direction. Now let's add a cap, for example. So from vessels and from elements, let's add a cap. So let's add here a cap. And this cap, let's make it as a standard cap, the standard cap, the same size and same schedule. And now let's make it flipped to flip the direction of this cap and click save. Now when you click start assembly, you can figure that the cap will complete in the same direction. Now if we take print screen and come back here, now you can see that the direction of the assembly started from here to there. Okay. After that, we flip it to be from here to there. Okay, so by that way, you can flip the direction of the assembly by using the flip feature. Now, if you would like to make an offset for an element, make it offset from the same center line of that one. Because here, as you can see, we have a center line for this element. So the center of elements will be aligned. So if you would like to make a shift for this element, which is this head, for example, make it shifted up or down, not centered with this element. How to make that? By using another feature, which is offset, like here, after selecting the vessel and from gap, let's select shift 1. Now from the shift node, let's select shift type and define an offset. Let's make it millimeter and keep the orientation as 0. Now let's click on save. And this shift, we will make it between the connection point here. The shift, we need to make it between the head and cap. We need to make the shift here. So the shift point should be between the head and the cap and the pipe. So we need to move this one. So let's select the shift and from move, make it move before cap. Select cap and click move. Now the shift point will be between pipe and cap. Now let's click on start assembly. And here, as you can see, we make a shift for the head from the center line. So something like that, you can use it in a sample like this. We create it for the wind turbine. If you open this one for this video, for example, here for this type, you can make a wind turbine by you can make, as you can see, it's one vessel as an equipment. You have a construction here for this part, so you can make start your. If we take an image for this and come back here, so the direction of sorry, here, for example, here the simply start from here to there. Okay. After that, you can offset this the center line from here to there, so you can start make an offset. After that, start your another arrangement, and when you come back to this point, you can move from here to there and start your assembly in that direction. After that, you can move from here to the third one and start your assembly. So by using this concept, which is offset and gap and shift and overlap, you can make arrangement like that. So if you take a look to that one, here you have the construction of the tree, and when you start creating this element, you will get the assembly like that. And from the end of this shell, you can make an offset from end point here to one of those ends to create another one. So by that, you can generate an equipment using the same concept of shift, move, and shift, gap, and overlap. Okay, now let's discuss another concept for the Unreal elements. Here for the Unreal elements, you can use this concept to create an attachment to a child, like adding a nozzle to another nozzle. For the concept of main elements, the main elements only the elements that you have the ability to add attachments to it. But the childs like saddle, skirt, nozzles, those elements not include any childs or sub-childs on the sub-elements. So to give you the ability to add a child to another child, you can make that by using the Unreal elements, and we will discuss that in detail by discussing the different cases, inshallah. Another case which is Unreal nozzle to as a fitting. If you have a nozzle connected to shell, for example, and this nozzle not from pipe or from plate, it's a reducer or an elbow connected directly to the shell instead of a pipe or a nozzle from plate. So you can use the Unreal nozzle to make this connection. Another type, which is make Unreal element to add the childs to another main element, but this the main element not include sub-elements in SEG library, and we will discuss that by making a sample. Here the first sample, if you have a skirt connection, if you have a skirt and you would like to add openings to this skirt, here you have a skirt, and this skirt you would like to add vents, add a nozzle opening or nozzle access, add a nameplate to this skirt, add insulation clips. So by that way, add earthing bows, for example. So here this access, this skirt not include any attachment in SEG3. So now let's discuss that on a real sample. So from here, let's from Edit tab, let's reset inventor model. This button gives you the ability to delete all inventor items in your project. If we take a look to the project. Let's close that. And if we come back to the project file here, which is GAB, you can figure that all assemblies will be generated here. Here we have one assembly for the vessel. Okay, we have the assembly here. And 4 parts, we have all parts inside this project, like this head, this cab, cone, and shift point or gap point. So if you would like to delete all items, and like that case, we would like to discuss the case of skirt and ellipsoidal head. In that case, let's remove all items. So from reset inventor model, you can delete all inventor items. If you take a look again to the project, no parts, no assemblies inside the project. So by that way, we delete everything. Now let's create a new vessel. To create a new vessel from GAB, let's right click and create new vessel. Now let's make a vessel called ABC like that, and click add. Now we have a new vessel. By that way, you can delete the previous vessel. So let's select ABC and click on delete to delete this vessel with its content. And from here, we have a new vessel called ABC. Now let's add an ellipsoidal head. From here, let's add, and let's define the inside diameter of this head as 2 meters head with millimeters the thickness, straight flange 50, and minimum thickness after forming like that, and click save. And now let's add a skirt. So when you select this main element, you will be able to add sub elements, which is called childs, to this main element. When you select the vessel, if you like that, when you select the vessel, automatically the elements tab will be changed to the main elements. Because when you select the vessel, you can add the main elements. But when you select a child, or a main element, sorry, when you select a main element, you will be able to add a child on that element. So here, let's select the head and let's add skirt. So skirt. From this skirt, select a skirt defined by ID. From here, let's define the ID as 1,900, like that, and the bottom diameter same. The thickness, let's make it 8 millimeters. Let's keep the information here as they are. Let's change the bottom width to, let's make it 200, and height 300. Top width 100, and now let's add a top plate, the width and radial length of that one. Let's make that one radial length. Okay, now let's click on save, and now let's start the assembly. Okay, now we have this head, and the skirt will be created and attached to this head. Okay, as you can see here, this element, if you select it from the tree, which is a skirt, for example. If you select it and open the elements tab, because it's a child, you will not find any elements here on this this child. You will not be able to add any other attachments here. So if we take a look to that part, and let's take an image, and from here, if you would like to add here an opening, let's try to add an opening here. We need to add an opening and another axis, or another opening or nozzle opening, add an axis to this skirt. So how to make that? By using the Unreal Elements concept. Here, if you let's imagine that we have a shell here. If you add a shell here after this head, but this shell takes the same information of the skirt. The same skirt inside diameter, the same skirt thickness. So at the end of this head, you will create an element with the same information of the skirt course. Okay, after that, you used this element to add nozzles, but the nozzles will not be on a positive location, it will be in a negative location. So in that case, you will be able to add elements to the skirt. So let's try that from by selecting the vessel node from the tree and selecting the shell node and creating a connection. Okay, and this connection point, you can figure that it's a shell, but we will not select one of those. Let's come back down here, and you will find two types here. One of them is called connection point for nozzles as a pipe. Another one, connection point for nozzle as a shell. In that case, because this skirt defined it as a blade with a longitudinal welding line with inside diameter 1,800 and thickness 10 millimeters. In that case, we will add a connection point as an unreal element, the same data of the skirt course will be like that, and the thickness will be 8 millimeters, and let's click save. Now we have an unreal element as we said from minutes. Let's imagine a part here as a shell, okay, but it's not a real element, it's just real element as a shell at the end of this head, and we will use it to add elements on this unreal element. So from here we add a connection point after the head, and when you click on assembly, you will not find any change on the 3D model. No elements created here, but we have a connection point here. This connection point looks like it will give you the same behavior of attachments on the shell. So now let's add another element to this one, like let's add a nozzle vent or a vent axis vent. So from here, let's add a nozzle with internal and external projection and name this one as vent 1. And from here, when you select this nozzle, you can define it as a nozzle from pipe with internal and external projection. Let's select the size as 4 and with a standard scalable. And the location here. For the location, as mentioned, if you add it with the positive value, the location of nozzle will goes in that direction. But actually, we need to locate it on the skirt. So the location of this nozzle will be located on the other side. So it will be with a negative value from this datum line. So here, let's define this value as with a negative value, 400 negative, with a negative value here, 400 millimeters. And let's keep the orientation at 0, no problem. And from here, let's make the outside projection as 50 millimeters and the inside projection as 50 millimeters. And here, let's add vent. And let's click on save. Now, when you try to create this attachment, we will get an opening like that. On that degree, okay, and located on the skirt, and the projection of this part will be 500 millimeter, and from inside, if we take a look from inside, so this type with internal and external projection. Now let's add another opening. So from here, from the connection point, let's select nozzle with internal and external projection, and name it axis. Okay, now this axis, let's make it with a rectangular opening, not an oval opening. Let's make it a rectangular opening, and let's make the length of this one to be 500, for example, and the width, let's make it 300, thickness, make it 8 millimeters, and the location, as discussed, make the location with a negative value. So let's define this as like that. And the orientation, let's make it in 90 degree. The projection, let's make it 100, and external and internal to be the same. And here, let's click on save, and from assembly, let's start creating the assembly. Now we have this opening as a rectangular opening, and if you would like to add a reinforced pad for this one, you can do that. So let's add a reinforced pad to this nozzle or this opening, like that. So you can add attachments to, as you can see here, the rebad located to the skirt exactly on the skirt outside diameter, because the here the connection point that we define takes the same information of the skirt. It's the same inner diameter and the same thickness of the skirt. So if you add an element here, it will be located and it takes the same dimensions of the skirt. Now, if you would like to add another attachment to this one, like adding a nameplate or adding insulation clips, you will be able to add that. So from here, for example, if you would like to add nameplate or fireproofing clips, here for this one, you can add fireproofing clips like that. So let's define this height as 600, 400, and thickness. Let's remove the chamfer, and the location, let's make it located on -400. Start at 10 degrees, for example. No overall thickness, or and that's the whole diameter and spacing. And let's make it with let's make it with 6 items on the circular pattern. Now, when you click on Start Assembly, you can add something like that, but the dimensions is not correct. We need to re-edit or modify the dimensions of this one. So from here, sorry, let's make it that one 40 and minimize that one like that. Click on Save. Now let's start editing this item. So the clip dimension will be like that. So by that way, you can add attachments to the skirt. Okay, now let's discuss another type of unreal elements. Here, if we so in this slide, we discuss how to add unreal elements to a skirt, for example. Now, how to add an attachment to a nozzle. If you have a nozzle and you would like to add another connected nozzle or a connected coupling to this nozzle, sometimes you have a coupling to add an instrumentation tool to measure the temperature or temperature. So by the same concept, you can add at the end of this nozzle, you can add unreal element, looks like, and it takes the same information of this nozzle. So by that way, you can add an attachment to a nozzle. Let's try that. And from here, let's reset the inventor model. And from edit, let's reset inventor model to delete all parts. From here, let's delete this connection point, delete this head, and let's add a shell and one. And from here, let's keep the can dimensions as it is and make the length 1 meter and click on Save. Now, if you try to add a nozzle, when you select the can node from the tree, you will be able to add attachments to this can. So here, when you select the vessel, as mentioned, you will find the main element. When you select a main element like shell, you will find the attachment of this main. Here, we would like to add a nozzle. So from here, let's add N1. N1 here will be as a nozzle, as a pipe, as 20 millimeters with a rebad. Okay, and let's make this rebad width like that, and the projection, let's 500 millimeters, And when you click on assembly, let's change the location of this nozzle. So from here, let's change the location to be at the mid length of the shell. Let's click on start. So the location here changed, and now you would like to add a coupling to this nozzle and add another nozzle. So how to make that? By the same concept, if you select this nozzle, the nozzle load from here, you will not be able to add elements here. Okay, so to be able to make that, you will need to select the external point, and from here you will add connection. And when you select the connection one, you will need to define the information of this node as a connection point, the same information of this nozzle. Here, this nozzle is 20 inches pipe with a schedule 40. So from here, when you come to this connection point and come down here to those types, which is they are the unreal elements, you will find a nozzle as a shell or a connection point as a shell or connection point as a pipe. From here, you will select this node and define the size as 20 millimeters and the same schedule of this pipe. Now, when you click save, you will get a connection point at the end of the pipe. If let's take an image from here and back to this point. Now we create an unreal element at the end of this nozzle like that as another pipe, but without any information, without it's not included in the bill of material. And now you would like to add another nozzle. So the same concept, you can use this unreal element to add a nozzle with a negative location. And like that, if we select this connection point and try to add nozzle N2, it's nozzle N2. When you try to add it with the same name and click add, you will get this information that you have the same name on the tree. So change the name to N2. Now we have nozzle N2. Let's make it a nozzle from pipe. Change the size to 6 inches. Schedule 40, for example. Let's add a repad, and the location we will define it with a negative value. But let's add it with a positive value. Let's add it with 200 millimeter to that, and the projection, let's make it 150. So the location here with a positive value. So when you create it, it will goes out the nozzle, not located on the nozzle. Now the second nozzle will be generated. As you can see, the location of this one, if we take an image here, that here, you can see here that the location of this one start from here, as mentioned, to the center line of the nozzle. So the 200 millimeters start from the end point of nozzle to the center line of this one. Actually, we need to move it back. So the location should be with a negative value. So let's change it to negative and click on save. Now, when you click start, the nozzle location will be located at that point. Okay. Now let's add a coupling to sub nozzle to the nozzle. We have a nozzle N2 here. Here we have nozzle N2, and let's try to add a coupling to this nozzle. By the same concept, we have this nozzle and we have a connection point here. So let's add another connection point. So connection 2. Okay, and this connection point should take the same information of this nozzle. So nozzle N2 with 6 inches size and 40 schedule. So from here, let's come down here and select connection point as a pipe. So let's select the size 6 inches and the 80 millimeters schedule. Let's check that again. It's 6 and 40. Sorry. So let's select this one as 6 and 40. The same schedule, and size. Now you can add a coupling to this connection. So from here, let's select coupling, connection coupling, one. And on this coupling, let's make it as a half coupling with rating like that, and change the size of this coupling. And the location should be with a negative value. So let's make it negative 50 millimeters and keep the orientation. The projection, let's make it 50 and click on save. Now when you click on start simply, you will add a coupling to a nozzle as a sub nozzle. Now we have this half coupling connected to this nozzle by using the same concept of unreal elements. So during this step, we discuss how to add the unreal element, to use it for skirt, how to use it on a nozzle, and now another concept for unreal nozzles. Okay. So here we discuss the unreal main elements, which is shell, and here unreal elements for as a nozzle. Okay. You can use this type of unreal elements to connect a nozzle. And actually, the nozzle type, you can find it as a pipe or blade or a forged hub. But sometimes, in some cases, you may need to connect an elbow or a reducer or any other type as a connected element to the shell. Here, the nozzle connection start to be as an elbow or a reducer instead of a nozzle as a forged hub or a pipe or a nozzle from blade. So how to do that? So in that case, we will check the ability to use connection nozzle point. So here, let's reset the inventor model. So from edit, let's reset inventor model, and from nozzles, let's delete those nozzles. And now we have this can, and from elements, let's add a nozzle. Okay, so make N1. And for this N1, we will not select one of the nozzles at the top. Let's come down here, and you can figure that you can add a nozzle connection from nozzle connection point. So this nozzle connection point give you the ability to add a nozzle as unreal nozzle on the shell, and this nozzle you can connect a reducer or elbow or any other item to this element. Here, for example, let's add this nozzle. Okay, you can define the size of this one. Sorry, again, let's go down here and select a nozzle connection point and define the estimated diameter of the shell. So let's make it like that. Define the thickness, the location. Let's define the location to be on the middle, the orientation 180. Let's keep the projection as it is. Now, when you try to add, when you create this assembly, you will have this shell, and you will have a connection point here for nozzle N1. If we comes down here, you will find an endpoint located here. This endpoint will give you the ability to connect elements with this point. Okay, so this endpoint, which is the located at this area, okay, at the end of this nozzle. So you have an unreal nozzle, you generate it and make the end of this nozzle located here. So from this point, you can add elements. So let's select the external connection point and add a reducer. So N1 reducer. From here, let's select a standard centric reducer. Define the size of this one and schedule the end size and schedule, and click on save. Now when you click on assembly, you will generate a centric cone like that at the end of the nozzle. So by using the technique of unreal nozzles, you can make other connections to the shell, like adding a reducer or an elbow. Let's try to add an elbow by the same concept. Let's select the shell and add another nozzle like N2. For N2, let's make it as a connection point. Define the shell inside diameter, and that's the thickness, the location, and let's keep the orientation as it is. Now at the external connection point of this one, let's add an elbow. So N2 elbow, and from here, let's select elbow with 90-degree and longer radius, and let's define it as 6 inches. Select the schedule of this elbow. Now, if you click on Start Assembly, you will create a connection point. Sorry, I defined the inside diameter with a huge value, so let's come back to this one. Sorry, let's remove this value, make it 980 instead of 9,800. So like that, by that way you can add an elbow connected directly to shell instead of a nozzle. And after this elbow, you can make another connections. Okay, so here for the concept of connecting elements to each other, on the connection point of the nozzle, when you let's take an image here, and if you take a look to the construction of the tree here for the nozzle, if you take a look to the nozzle, you can figure that this nozzle includes an external connection point. That's in case if you select a nozzle with external projection. You will find an external connection point. This point you can add items to it. Like for example here, after the reducer, you would like to add another element here. For this reducer, if we select this reducer, the end reducer size is 6 inches. So if you select the external connection point and try to add another element like N1 pipe here, so you will have a pipe after the reducer. So you can define the pipe size as 6 inches, the same schedule, and let's define the length of this pipe like that. So when you click on Start, you will get a pipe after this cone. So by that way, here you can add, by the same concept, you have at the end of this reducer, you have a start UCS and end UCS. As you can see, you have end and start UCS, and the pipe includes the same at start and end. So by the same concept of the user coordinate system, you can make an arrangement for elements at the external connection point of the element. And inshallah, after minutes, we will discuss that in detail by using the T and check the T options here for the connected T and how we can connect for the branches of the T. Okay, now let's go to the next step. Here we discuss the unreal nozzle and how to connect an elbow or a reducer to a shell as a nozzle. Now, if you have an element like this type, which is conical head with closed end, and this type actually not includes any child. It's a main part, but not include any child. And for the aluminum dome roof, this type not include a child. So how to add elements to those parts by using the unreal elements. Okay, now let's check the first part, which is the a conical head with closed end. This type of head includes a part of a hemi head at the bottom here, and includes a part of a conical shape. And both of conical and hemispherical head, you can add attachments. So let's create a new part. So from edit, let's reset inventor model and delete this can. And from here, let's select elements, and let's create an ellipsoidal or a hemi head. From here, let's add head. And this head type, let's select hemispherical, a conical head with closed end. So you can see that you have more than 17 types, but we, in that case, to define the case that we have, we will select conical head with closed end. Let's define the inside diameter of this one as 2 millimeters. This as 20 millimeters. Straight flange is 50. Minimum thickness after forming, and here's the macro radius. Let's make it 20, and the crown radius, let's make it 500, and the height, let's make it 1 meter. Okay, and let's click on save. Now when you click on start, we will get this type of the conical head. Okay, as you can see, if we make a drawing for that, and let's get a view for this part. Let's increase the scale a little bit. Okay, here if we take a look to the to that point, let's increase the crown radius a little bit. So here, let's make it 200 like that. Okay. And when we come back to the drawing here, you can figure that we have a cone, the same configuration of a cone, start from here and end at that point. Okay, and we have a part of sphere, okay, or a hemi head like that. Okay, we need to add nozzles on that part of the hemispherical contour, and we want to add the nozzles to this conical shape. When you select this part from the tree and select elements, you will not find the nozzles or attachments to this head except platform. So how to add an attachment? In this case, we will use the same concept of unreal elements to add a hemispherical head to the end of this conical head with closed end. Okay, now let's add a nozzle to this hemispherical part by the concept of using the unreal element and the overlap element. Here, as you can see, the user coordinate system at the end of this head locate for this head the end UCS located here, okay, at the end of this head, and we need to move this user coordinate system up to the center of the hemispherical head and create here an unreal element as a hemispherical head to be able to add elements at this point. So if we make a sketch here and create a circle, start at this point. So if you make a hemispherical head at this area as a unreal element, you can imagine that you have a head here. By that way, you can add a nozzles to this head. Okay, let's try that in SEG, how to make that. At the first, let's make an overlap point. So from here, let's select the vessel and make overlap 1. From the overlap, let's define this type as overlap with that offset, which is 500. So from here, let's make the overlap as a 500. And now let's click Start Assembly. Now we will get this overlap point, and you can figure that the end point, the end UCS comes here, which in the same place that we need, which is the center point of this sphere. Now let's add a hemispherical head as unreal element at this point. So from elements, let's select the vessel, and from head, let's add connection point for hemi head. And this connection point, at this connection point, let's come down here and select that type, which is connection point as a hemi head. Okay. Now let's define the inside the diameter of this one. As you can see, the radius is 500. Now the diameter is 1000. So the inside diameter is 1000, and the thickness is the same thickness of this one. So the thickness here is 20 millimeters. So let's define it to be 20 millimeters and click save. So here, if you imagine that, we will make a hemi head looks like that. Okay, and we will use it to make or create a nozzle. Now let's save this, and let's select this head and create a nozzle. So from here, let's create N1. And from N1, let's select it as a long weld neck nozzle, for example, or a nozzle with a rebad. And let's define it as 4 inches with a rebad, millimeters. And the offset of this one, we check the center line. So you can, by using the center line option, let's add a center line from here to there. Okay, so from here to the end at that point, it's 300. So if we make it with 150, it will be located on the middle. So we can make it like that, and the orientation keep it 0, and the projection, let's make it 150, and click on save. Now, if you click on Start Assembly, now the connection point will be created as a hemispherical head, and the nozzle will be generated and located on this part of head. As you can see, the contour of the nozzle located in correct location on this head. If we open the drawing again here, you can figure that this nozzle located on the correct place. If we measure the offset from here, which is 150, okay, we have this nozzle located on the correct direction on that head. Okay, and you can you have many options. Inshallah, we will discuss it, like make it this nozzle radial or parallel to the center line or tilted with a defined angle. Those are some options we will discuss them, inshallah, in detail for the nozzles. Now we need to make another nozzle located on the conical section here. How to make an unreal conical section? Okay, this unconical section you can or the conical section, you can use it if you have a skirt with a conical configuration, not a straight skirt. Here on that slide, here we discuss a conical, a skirt with start and end diameter the same, straight skirt. But in case if you have a conical skirt, okay, and you would like to add opening or something like that to this conical end, so in that case you can use the unreal conical element. Okay, so how to add a conical element here? By the same concept, we have the end UCS at this point. We move the UCS from the end of the cap. So let's take a print screen from here. Okay, so the end point of this cone falls here. Okay, let's give it a red color. So we had the origin point or the end UCS here. After that, we move it forward to this point. So we get the UCS up to this point. Okay. Now we need to create a cone. So we need to move back a little bit from here to there. Okay, to make let's say another UCS at this point. Let's change the color. We need to move the end point or the UCS from here to there to make a cone. Let's imagine that we have a cone here, start from here and end there. Okay, so we have a cone at this space. So the cone starts from here up to there. So here the first thing we need to do to move from this UCS up to here, after that create the unreal cone. Now let's add another overlap. So from here, let's select overlap 2. And this overlap, we will give it the value from here to there. So from this center point, let's add center point here. So from this center point to the end here, we have this value, 331.74. So here, 331.174. So the overlap will take this value. Now let's click on save. And when you click on start as simply and come back to Autodesk Inventor, we will get overlap 2. And when you check the end point here, you can figure that you move the end point of right here at the start of the code. Now let's add a conical shape as unreal elements. So from elements, let's add a cone. So add a connection point as cone. Okay. And from here, you will find a connection point as a centric cone. You can select it. Now let's define the dimensions of this cone. What is the dimensions of this cone? So here, that's the start inner diameter of the cone. And here, the end diameter of the cone. And that's the height of the cone. So we need, and the same for the thickness. So those are the 4 values for this cone: the start diameter, end diameter, length, and the thickness. So we will make an unreal element with the same dimensions of this part of cone. From here, that's the start diameter, 748.2. 748.2, that's the start diameter, and the end diameter, 189928. 189928. And the length is 649.04. 649.4. Okay, right, yes. And the thickness is 20 millimeters. Now let's click on save. And when you click start simply, we will generate Unreal element to use it as a cone on that area. Now let's add a nozzle to this connection point. So from here, let's add N2. And from N2 here, let's add a nozzle from pipe. You will find a different type of nozzle, but let's select a nozzle from pipe connected to cone. And let's make the size of this one as 10 inches. Let's add a rebad, change the scalable of this one, and the location of this one. If we take a look here, so we need that's the length of the cone. If we make it on, let's say, let's keep this location at orientation 0 and keep the projection. And now you will make it perpendicular to the center line of this cone. So the direction will be perpendicular to the center line of the cone, and you can make it parallel or tilted or radial. Sorry, you can make it radial, perpendicular, or parallel to the center line. Now let's save that and click on start creating the this nozzle. So you can figure that you have this nozzle located on the cone by that way, okay, and it takes the same configuration and the contour of this cone. We take a look here. You will find this nozzle up to the end of the thickness of this cone like that. Okay, now let's discuss another. The same option, you can do it for the dome roof by using the hemispherical head. So the connection point as a hemispherical head. You can make the same thing if you would like to add attachment to the dome roof. Now let's discuss some other options regarding the some of common mistakes, and we need to avoid making it during creating our projection. The first one, which is selecting names for the project, and the name include illegal characters like a backslash, question mark, or star. So if you try, for example, to create a new folder on the desktop, and this new folder includes one of those illegal characters like backslash, when you try backslash, that or comma, or question mark, you will not be able to create a file including one of those characters. So if you try to create a new project, like from here, let's create a new project, and from here, let's add a project with name 123 and backslash, question mark, and star. Okay, so you have legal characters here inside this name. So let's select the location and click on save. Now, if you try to click finish, you will get this message, which is here. If you try to create a name with illegal characters, you will get this message which inform you illegal characters in path. So SEG will not be able to create this file because the Windows itself will prevent that. Okay, because of illegal characters. So that's the first mistake you may do. So we need to avoid using illegal characters on project name or tree name. So by the same way, you shouldn't add element here with legal characters. Like if you add element here like that and add backslash here, when you try to add something like that, SEG will prevent you from making this. So you should avoid making illegal characters on the path of during creation of the elements. Okay. Now renaming the project folder by hand. That's one of the most common issues here. After creating a project, sometime you may need to create another project. Looks like the current project. You have the same tank, but with different information like thickness or 10 to 10 or inside diameter, but it's the same or near from another vessel, and you would like to take a copy from an old project to create your new project. Sometimes you may fail on this mistake, which is take a copy and make a rename manually. Okay, if you make a rename for this project manually, you will get an error because the information inside the project itself defined it for the old project name. Like here, let's try to close this project. So from here, let's close SEG. Okay, and from here, that's the project name, which is GAB, and as we discussed, the SEG file will take the same name, which is GAB, and inventor file takes the same name. For example, when you take a copy from this one, let's take a copy, paste it here. And this project, let's name it as a new GAB project, new GAB, for example. That's the new project name. So here we take a copy from this project and make another copy with another name. If you take a quick look here, the name of this project not looks like the same name you have here, name GAB, but here the SEG file with another name and the project file of the Autodesk Inventor with a different name. Now, if you try to open this project, so let's open SEG. And if you try to open this project, so from open, let's go to this project, which is new gap, and open this one. As you can see, the name here is different from the project folder. When you click on open, okay, you will not be able to, let's try to add an element here. Sorry, I may open another one. I think I open another project, so again, please. Okay. If you make this one by that way, by making a rename for the project manually, you will get an information missing during creating your project. Let's try another thing by making a rename for all parts here, for all nodes here inside this folder, like renaming the SEG file. So the naming here, you did it manually. So let's rename all related files manually. And when you try to open this project, like that one, and try to add a new element, that one, you will get this message, which is inform you, you will not be able to add a new objects. That's because the project name includes another name. And to avoid that, so here you will get those messages during creating a new project or a new element in case of making a rename manually. So to avoid that and how to make a copy from your current project, so let's close this one. Okay, and let's open one of the other projects, which is Gap. Let's open that project. Now you will find a tab here, which is Save As. Save As will give you the ability to create a new project with another name. And SEG, in that case, will make all needed changes during saving. So to take a copy from a project with another name, you should make a Save As. So let's make here project, and let's click Finish. Now it's saved successfully, and if you click on Open, you will find a new project here created on the desktop called Test Gap Project, and you will find all required files takes the name, the same name of the project file. Let's close this project. Okay, one of the other issues you may face, which is saving or mistakes you may fail on it, which is modifying element and save it during running. Here, if you try to, let's open SEG again. Let's open SEG. Okay, and let's create a new project. Let's select overlap, define this project, which is test project, and select the location of this one. Select the module. Now click Finish. Now let's add a shell here. Okay. And let's find the dimensions of this one. Length. Click Save. Now let's add a saddle to this skirt, like left saddle. And saddle. Let's add many items to this saddle, like outer ribs, mid ribs, intermediate ribs. Okay, and keep the other information as they are. Now, to check this point, which is modifying element and saving during creation. Here, when you let's open the app setting and activate the child preview and parent preview. Those options give you the ability to make a rendering for elements during creation. So after selecting them and click on save, now when you select the assembly and start the assembly, you can figure that if you come back here, the start button now disabled and the stop button now enabled. If you come back to Autodesk Inventor, you can figure that here the saddle now assembled and created and assembled. So during this creation, if you decide to change the location, for example, make it on 500 millimeters and try to save this file during creation, it's still created. And when you click on save, you may cause a problem for this file, because during this step, SEG sending information to Autodesk Inventor and receive information from Autodesk Inventor to store it inside SEG file, like getting the weights, getting some dimensions for this saddle. So if you if you click on save during sending commands to Autodesk Inventor, you may cause a problem in SEG software. So to avoid that, if you here, for example, you would like to create another element connected to this shell, but you would like to stop the assembly. Let's add another saddle. So here, let's add, let's say, a cone. So from here, let's add another can 2, and let's make it looks like can 1, another can, or another head. And flip. So from here, select spherical head, diameter, and flip it. Now, when you create the assembly and try to stop it, so from here you can click on stop. So stop option will give you the ability to stop the assembly after finishing the modifying on the current part. Here we change the location of the saddle from 400 to 500. So the first thing is you will start modifying the location. Okay, after that, the assembly will stop. Okay, because we click on stop button, so you can figure that SEG stop the assembly without creating can 2 or head 2. But that's after clicking on stop button. Now, if you click start, SEG will start creating this saddle and click the can. If you click on stop button, SEG will start creating the next part, which is can, like that. After that, if you would like to stop, you can stop this element after creation and it will not be assembled. Here you can figure that this head added to the assembly but without assemble it. So to stop the assembly, you can use stop button to stop the missions that you are doing in that time. After finishing this mission, which is creating the current part, the SEG will stop the assembly after finishing the current mission. Okay. Now that's one of the common mistakes, which is saving during editing. Another issue, which is selecting another node without selecting a proper element. Like, for example, here if you select the now you can figure that we select the text of the can 1, but you can see on the drawing area here, let's print screen. You can figure that we select the can text, but you still receiving the design data, which is related to the vessel, not the can. So that's one of the common issues. You should select the icon of the element, which is the can. So when you select the icon of the element, you will get the correct information or the correct drawing area for the element. Like when you select the equipment here, when you move, sometimes you should select the icon to get the correct information for the element. Here, making an element same another element after creating over Autodesk Inventor. Here, for example, let's create a nozzle. Let's delete those elements. Okay, and let's reset Inventor model. Okay, and here let's create a can tool or pipe. And let's make this one as a pipe, not a shell. Okay, and now let's create those. So we have a shell from blade. After that, we have a pipe after this shell. As you can see, the end point of the can will be connected to the start point of the next element. It will be like that. Now, sometimes you may decide to change the type of this pipe, and you may select it from the tree, and from Save As button, you can change it, like can make it as a can one. So the properties of this element will be same as can one. So you will convert the type from pipe to shell. And when you click on save, now if you move to another point and come back to this pipe, you will find the same, the information of this node changed from a shell to from pipe to a shell. Now this mistake may take place when you generate the 3D model. In case of you still not generate the 3D model, nothing will take place. But here, after creating the 3D model, when you click on Start Assembly, you will get an issue during the creating of this part. You will not find it updated. Okay, so to reflect that or to update it, you have two ways. The first one is resetting the inventor model. So by resetting the inventor model, when you delete everything again, the this pipe will be generated to looks like the previous element, or by selecting reset inventor item. Now you can figure that the shape. Okay. One of the other mistakes, which is elements may sometimes stuck in the memory, and to release that you may need to close Autodesk Inventor and SEG. Now let's try to change the type of this part. We have a pipe here, and this pipe is as a part. You can figure that, and we discuss the difference between the part and assembly, and we know the difference. Here you have a part as for this shell, and now you decide in to change the number of the segments for this shell to be from 3 segments instead of 1 piece. Now the type of this part changed from part to assembly. Now if you click on save and start the assembly, here SEG will delete this part and start creating the new element as a shell. Here, as you can see, SEG deal with that and change the part. And sometimes Autodesk Inventor still store inside the RAMs, the running memory, some information, and SEG cannot release it. In that case, SEG removed it and replaced the new part. But in sometimes, when you try to make that, like in this assembly, let's try to change it to a pipe again. So from here, let's make it a pipe and make it 24 inches and click on save. Now let's try to start the assembly. Here we change it from pipe from assembly to part. Let's change it again to another shell type. Keep the information as it is, Now let's start the assembly. As you can see, sometimes SEG can reset the information and modify that. And sometimes, as mentioned, you may face an issue regarding that. And when you close SEG, now let's close SEG and open it again. So let's close this project. Okay. And let's open SEG again to check if we miss something or not on the model. Let's open this model again. Which is test project. Yes, a test project. Now, as you can see, you have the 2 nodes on the tree, and if you try to open here we have everything is okay. But sometimes during the information stuck on the memory, you may lose this part. To create it again, you can select this part from the tree and click on save, and from edit click on reset inventor item to delete this part and create it from scratch again on the assembly of this equipment. Okay. So those are the most common mistakes, and we need to avoid making them during the creation. Okay. Now, inshallah, we will create a new project and discuss some important points regarding the connection and elbow connection, and how you can make a nozzle with internal and external projection, and how to make something like that. Now, from here, let's from file, let's create a new project as a demo. Okay. Click location for the project and select a vertical bezel. Okay. So here on this the session of today, we are talking about the concepts of SEG and how we can deal with the model, how to add elements, modify on elements, all of that. Inshallah, on the next session, we will make, inshallah, a complete storage tank, and we have enough time, we can make a detailed drawing for the tank in detail, inshallah. Now, from here, let's select this one and select head. Let's keep the information of this head as it is and make it flipped. Now let's start the assembly. Now we have this ellipsoidal head, and it's a bottom head. Now let's add a nozzle to this one. So from in here, let's add N1. And for N1, let's define it as a nozzle from pipe. Let's make the size as 12 inches, scalable 80. And the offset at 0 with a rebad. And let's make it, you can make it sit in or sit on. You can make it radial, parallel, or tilted, so you can control the angle of tilting of this nozzle. And when you click on save and create this nozzle, as mentioned, if you would like to make a rendering for elements during creation, you may need to activate the options on the setting, which is child preview and parent preview. Those options will give you the ability to make a rendering for elements during creation. Here we have this nozzle opening, and let's add an elbow at the end of this nozzle. So if you take a look to the tree here, SEG tree, you can figure that you have a connection point here. Okay, that's the external connection point. this connection point, if we take a look to this nozzle, that's the nozzle, you will find end UCS here at the end of this nozzle. Okay, this UCS or this end connection point give you the ability to connect or attach elements at the end of this point. So if you select the external connection point from here, you will be able to add elements to the end of the nozzle. Okay, to the end of the nozzle, not on the nozzle itself. Okay, to add attachment to a nozzle, we discussed the concept of unreal elements, which is we discuss it here by using unreal element as the end of the nozzle to add attachments to this nozzle, like a nozzle over a nozzle or coupling on a nozzle. But to connect elements at the end of this nozzle, you will need to select the external connection point, and from here, let's add an elbow. So N1 elbow. And here, this elbow should be the same with this nozzle. This nozzle is 12 and 80. So from here, let's long radius 12 and 80, and let's click on save. Now you can see that you have the ability to connect this elbow to the end of the pipe. Now let's click start. Here we have an elbow connected to the end of the pipe like that. Okay. By the same way, you can connect another elements to the end after the elbow by selecting the external connection point, and from here you can add a reducer, for example. So N1 reducer, and from this reducer here you can, for example, select eccentric reducer, eccentric cone, and define the start diameter as 12 and the scalable 80 and the end radius as 6 and make it 80 and click on save. So eccentric angle, you can make it, you have the ability to change it. But right now let's save it as it is, 190 degrees. To check the direction of this eccentric cone, here you have this eccentric cone like that. So the eccentric angle at 180 degrees, so it will be at the bottom here. Okay, and if you have the ability to change the orientation of eccentric angle from here. Now let's add another pipe after this eccentric cone, like here. So N1 pipe, and from here let's make this pipe with the same end of the eccentric cone, 6 inches, 80 degrees, and the length of this pipe is 200 millimeters, and click start simply. So we will get a connected pipe to the end of this eccentric cone. As you can see, you make a piping connected to the end of this nozzle pipe that way. Okay, now let's check the ability to add a reduced T or equal T to another point, and how we can deal with the T. From here, if you select the external connection point, and from elements, let's select T. So N1 T. So you have a T here connected to the pipe. And from here, let's select a reduced T. Select the size as 6 inches, scalable 80, and the other size is 3 inches with, say, scalable 160, and click save. Now, if you take a look to here, look to this tree, let's zoom a little bit here. You can figure that this T here includes a branch and includes internal connection point. You have 2 connected points here for the T. On the nozzle, you have a single one for the external, like that. But on T, as you can see, because T has 3 exits or 3 inlets. Okay, so one of them will be connected to the previous point, and 2 connection points will be on the other side. So here, as you can see, as a default, you will get here a branch and inlet 2. And let's check this option, which is connected to branch from branch. That means that when you select this checkbox, you will connect the T to the previous element, which is the pipe. So here we have a pipe. Here you have a pipe before the T. So if you would like to connect this T from the branch, so if you would like to connect it from the branch with the previous part, which is pipe, you will need to select this checkbox. Okay. Now let's check the default options. Keep everything as it is. Click Save, and now click the Start Assembly. That means that T will be connected from one of inlets. Okay, and you will get. So you can figure that this T connected from one of its inlets, and the second inlet will be free, and the branch will be free, like that. So you can figure that you have a branch here, another inlet there. So if you would like to connect this T from the branch, okay, let's select the branch connection. So that means this T will be connected with the previous element, which is N1 from the branch. So let's click Save. Now when you click Start Assembly, before clicking on Start Assembly, if we take an image and create new one, sorry, let's create and then spin it. Okay, from here let's print screen. So you can figure that you have here inlet 1 and inlet 2 instead of branch and inlet 2. Let's take a look to the previous image. Here, when you deselect this option, you have here branch and inlet 2. But when you select this option, which is branch connected from branch, so the 2 exits here will be available to connect inlet 1 and inlet 2, because if we come to the 3D model, this branch will be connected to the previous element. Now let's click on Start Assembly. As you can see, the T now connects from the branch, and inlet 1 and inlet 2 now become free. Just we need to change the size of this T to suit the size of this pipe. So from here, let's change the size. Let's make it 10, for example, by 6 inches, and click on Save. Now when you click on Start Assembly, you will change the size of the T to suit the size of the pipe. Now you connect this T from branch, okay, and you have 2 inlets free here. And those 2 inlets, you can use them to generate or add, to add another attachments. Like, for example, here, let's add an elbow. So from here, let's add T elbow 1. Here, let's make it short radius, 90 degrees. And from here, let's select the size of the same size of T. And for this one, let's add elbow 2. Okay, save. And from here, you can make it looks like the previous T. So from here, select T2. So those T's will be connected to the end of as the inlet 1 and inlet. After that, we will change the orientation of the those elbows to suit your needs. If you require to rotate them, so you have the ability to control the orientation of the T. For example, if you would like to rotate it 180 degrees for this T, for example, and click on Start, the direction will be from the exit of this one will be to the bottom instead of top. So you can change the orientation of the T. The same for the elbow. You can change the orientation of the T itself. If you come back here for the T, you have the ability to change the orientation of the T. For example, let's make it on 90 degree, like that, and click on Start Assembly. So the orientation of the T will be like that. And by the same way, you can add connections to the elements. Like let's add a cone at the end of after the elbow. So from here, let's select used cone. So let's add the cone 1. Here. And from here, let's select the same size and schedule, another size and same schedule, like that. Click on Save. Now when you click on Start Assembly, you can make a connected elements to the end of this part, like that. Okay, so by using this technique, you can make a piping for the vessel inside or outside. Now let's add a shell element. Okay, so from here, let's add shell can1. And for this can1, it's a shell. Okay, and keep the data as it is, or we can decrease the height a little bit. And from here, let's add a nozzle with this shell, but this type of nozzle will be nozzle with internal and external projection. Okay, so here, if you here on the first sample, we add a nozzle with external projection only. Okay, but here let's add a nozzle with internal and external projection. So let's add N2. And from here, let's define this nozzle to be, let's say, 10 inches with a rim scale 80, and the location will be 500. The orientation keep it 0. The projection from inside and outside, and click on Save. Now, when you click on Start Assembly, we will get a shell course. After that, we will have a nozzle on this shell with internal and external projection. Here, if you take a look here, you will find this nozzle with internal projection like that. You have internal and external points. If we take a look to the assembly of this nozzle, you will find the pipe here, and if you take a look here, you will find internal connection point. That's the end UCS, and another external UCS at the end here. You have a UCS at this point here, and another UCS at the end of this pipe, like that. Here you have a UCS here at the end of this pipe, and another UCS at the start of this pipe. So from those UCSs, we can start making an assembly or a connection to this element. For example, here you will find, if we take an image from here and create a new image, here you can figure that for the nozzle, for this type of nozzle, you will find internal and external, like that. You have internal and you have an external connection. But for the previous nozzle, you have external connection only. Okay, for the nozzle with external projection, you will find a single connection point at the end. But here you will find 2 connection points. So if you would like to connect from the inlet, you will select the inlet nozzle, the inlet connection point of the nozzle. And from here, for example, you can add an elbow. So into elbow. And let's make it with the same size. Let's make it short radius, 10 inches with the same schedule, and click on Save. If you click Start Assembly, you will create an elbow connected to the end of this pipe, like that. Okay, and let's take a section. So from view, let's take a half section, and make a half section like that. So you can figure that you have an internal connection for this pipe inside the vessel. And you can make any piping inside, like making a deep pipe. After that, you can add some other attachments to this deep pipe, like supports or any other nozzles with this deep pipe. So you can imagine what you can do by using those features. Okay, so here we discuss the ability to add connections to nozzles with internal and external projection, how to deal with the T, how to change the connection point for the T from branch or from the inlet. And for here, let's check one more thing for the coupling connection. Here, if you take a look, if we select the CAN, you will find two options for the coupling, which is coupling with a plug. Okay, so in this type of coupling, you will not be able to add elements to this coupling. It's an in the coupling, nothing to connect it to it. But if you have something and you would like to make a connection to this coupling, that means you will need to use a coupling nozzle. So here in this type of coupling, you will get an end point. That end point will give you the ability to connect a piping to it. For a quick sample here for that. Sorry. Here, let's open one of those samples here. That sample. Here you have a coupling here on this cap, and this coupling you will connect a threaded pipe to it. After that, thread elbow, another thread elbow, another valve. So here you have a coupling, and you would like to make a connection point to this coupling. In that case, you will use the coupling nozzle, not a coupling only. You will use this type. And by the way, this sample is one of the pre-built projects. So from here, if you open the template, so from file, if you open the template, here you will find this sample as one of the pre-built projects here, that one. So when you click on create, like for example, here, let's generate this project and create it on the desktop. Okay. Now the files of this project will be generated, and we will receive this assembly that template successfully created. Now let's open this project. So let's come back to the desktop and select this project. Okay, let's close this template. And here you can check the tree of this element. Here you have this head. You have the elements connected to this head, and here you have the coupling. Okay, and this coupling now include its print screen, and here let's this one. As you can see, this coupling here include an external connection point, so you can add elements to this connection point like that. You can add, as here and in this image, you can add pipe elbows and anything after that. You can, by the way, you have valves here on SEG library, so you can add some types of valves and manometer, pumps, and end closure. Agitator, if you have a storage tank, a vertical storage tank, or you can use agitator, by the way, to add a sample of agitator to your vessel. Okay, now let's go to another step, which is discussing the type of shells. Let's open the old project, which is this project. Okay. To discuss the type of shell. Now let's reset this model, delete the elements inside this tree, and now we will discuss the available types of the shell. Let's create a shell, because this part is will be shared with tanks and pressure vessels. So we will not discuss the type of heads in this session, but we will discuss the types of the shell. So from here, let's select the vessel, and from this one, let's create a new shell. Let's add CAN. Okay. From here, the first type you will meet it, which is a pipe. In that case, you can make this shell as a pipe. So you can select the size of this pipe from standard sizes of the pipe from 0.125 inches up to 80 inches. Okay, so the size you can define it from here. After that, you will find the outside diameter on the next text box, and you will find it disabled. So you will get the values in this text box. That is the outside diameter of the pipe. And here that you will find the schedule of this pipe. So when you select a schedule of this one, the thickness will appear here on this text box. And by the way, it will be disabled. Now, for example, if you would like to get a pipe without standard thickness, what can you do? Here you will find a checkbox here for the user-defined thickness. That means when you select this checkbox, you will be able to change the thickness of this pipe, and here you can figure that the drop-down list of the schedule become disabled. You will not be able to change it. So from here you can define the thickness. Let's make it 15 millimeters, for example. So this pipe will be 24 inches with a defined thickness as a 15 millimeters. And here you can define the length of this pipe. Now, when you remove this checkbox, let's make it 15 again. When you select to remove this checkbox, the thickness changed again to be equals the new schedule that you select. Okay. Now to change the material of this piece or this part, you can directly modify the material here, or you can open the material list. So from here you can select the table from the according to ASME section 2 part D. You can select the table from here and search for your material like SA 106. So you can figure that you have grade A, B, and C, and you can figure that that's the product form, a seamless pipe, and here the UNS number for this material, and all of them are a carbon steel material. You can add remarks for this material like some information regarding procurement or something like that. You can add the remarks for this part here in this cell. And if you would like to make it an impact listed material, you can select this checkbox, or normalized, you can select this checkbox. Okay, here after clicking on done, but after selecting the pipe, you will reflect the material on the text box. Okay, so let's change this one and let's create it. Okay, now we have, we will create a pipe or a shell from pipe. Okay, and if you open the bill of material for this part here, you can figure that the description of this part will be a seamless pipe. Okay, that's the description, and the technical characteristics of this part will be, let's take the screen and increase this view a little bit. So here you can figure that it's a seamless pipe, and the technical characteristics, it's NBS 24, and the schedule of this one is 20, and the length is 200 millimeters, and here's the material, and on the next cell, the weight of this element. Okay, so you will get the information of this element, including the weight, after creating this element on SEG and Autodesk Inventor. Now let's discuss the second type of shell. So from elements, let's add another CAN 2. In this type of CAN, you can add a welded pipe. So this pipe will include a longitudinal welding line. So you can define the orientation of this longitudinal welding line. and this pipe will takes the standard pipe diameter. Okay, so you can define the pipe diameter. Okay, and from here, by the way, you can make it as a blade, but here it will give you the ability to make it with the same diameter of the pipe. Okay, so you can figure that the pipe outside diameter will appear from here, and the pipe thickness, pipe length, all of that. The third type you can generate it, which is shell without welding lines. So this type you can use it in case of preparing an offer, for example, and you would like to make a quick 3D model without go in deep to make a detailing for each shell course and the orientation of welding lines. Like if you have an LBG, let's say for 40 or 50 meters the length. Okay, so you can make a one shell without any welding lines to represent the configuration of the LBG without going in detail to define the welding lines, locations, and shell plates. So from here, you can define this type of shell by that way. Now, one of the important types in shell, which is shell, the normal shell type. This type you can use it in pressure vessels, columns, and storage tanks, by the way. This type of shell give you the ability to make a manual, an automated calculation for the required number of shells. For example, here, if you have this shell, and if we open before modifying it, let's open the application setting and select the equipment from the tree. And from here, let's open the equipment setting to modify the some information here regarding the delivered blade dimensions. So for the length, let's make the length of the blade like 6 meters and the width of the blade as 150 millimeters. So that's the blade before forming. So if we open a new sample like that, that means you will get a blade with 6 meters length and 1.5 meter width. So when you make a rolling for this blade to get the shell diameter, in case of the total circumference length of this shell more than that value, okay, if the value of the total circumference of the shell more than that value, automatically SEG will calculate that and detect that you may need another piece to complete the circumference of the shell. Let's try that. For example, here, after modifying this, so that length may cover inside diameter maybe around 1,700 millimeters inside diameter. So if we increase the inside diameter, let's save this value and let's reset the inventor model. Let's remove CAN1 and let's modify on CAN1 directly. So from here, let's select CAN1, and from here, let's select the shell and make the inside diameter as 3 meters. Okay. So from here, you will find that if you make a quick calculation for that, and you can make it, by the way, by the calculator of the arc length from SEG. So the diameter, which is, as we discussed on the third, sorry, if we come back here and open the day 3 course. For that one, which is the K factor, when we try to get the natural or neutral line, which the defining the actual length of the part, actually we use it on 0.5 from the thickness. So here the inside thickness of this vessel, the inside diameter of this shell is 3,000 millimeters plus twice thickness. So we have 10 plus 10. So that's the outside diameter. So the mid diameter or the diameter at the neutral axis is 3,000 plus 10 millimeters. So here that's the neutral diameter. So to calculate the total circumference of the shell, we can use this diameter. So from here, let's inside this diameter and the angle, which is 360, to calculate the total circumference. Here you will get the circumference length, which is 9 meters 0.4 around. That's the correct value of the total required circumference. Here we defined the delivered blade dimensions to be 6 meters and 1.5 as a height. So when you try to make, let's say, a shell like that, okay, when you try to make one like this, and let's remove this part. When you try to make that one, so the height here will be, if we write a text here, sorry, the height here will be 1.5 meter. So the height here will be 1.5 meter. So if you try to increase this value more than 1.5 meter, SEG will prevent that. So let's change, keep the height here 2 meters 0.4. So here the available height 1.5. So if you try to make this height with 2 meters 0.4 and click on save, SEG will inform you that the length must be less than or equal the delivered blade width, which is 1.5 meter. So you should change this value to 1.5 meter as a maximum value. Now, if you try to click on save, automatically SEG will accept that. And by calculating the circumference length and the delivered blade dimensions, which is 6 meters, SEG automatically, when you try to generate this element, SEG automatically will detect that you will need more than one piece and directly will calculate the required length of the second piece. Here, you can figure that you will have this assembly, and if you open this shell, you will find the first piece and second piece. Yeah. Let's try the first to open the first piece. We have the first one here. If you try to get the sheet metal development of this one, and from measure tab by using the measure tool, you can get the length of this one 600 or 6,000 millimeters. Okay, as we defined on the setting information of the equipment. Now let's finish editing of this part, and let's open the second part, which is part 2 on the shell. Let's open part 2, and when you try to get the sheet metal development of this part and measure the length of this one, you will get the length of the remaining piece of the blade. Okay, so by that way, SEG directly calculate the required number of blades in case of using more than when the circumference length become more than the available blade dimensions. Okay, now let's try to make another option on this shell. So let's reset this model, and on this shell, let's use another option to make this shell from equal segments. Okay. So when you select this checkbox, which is enable segments, you will be able to define the number of segments for this shell. For example, when you make them as 3 from 3 pieces, let's change it longitudinal welding line orientation to make it at 0. Now you will make this shell from 3 equal segments. So when you click Save and click on Start Assembly and come back to Autodesk Inventor, now you will figure that you generate an assembly for the shell, and here you have 3 parts. Okay, that's the first part. Here, if we open it, and they all of them are equal. So when you generate sheet metal development and get the length of this one, you will get an equal length for all blades. So that's the development length of the blade, which give you 3 equals blades on this shell course. Now let's check another option for the shell. So from elements, let's reset the inventor model and go to another type of shell, which is shell to a hemispherical head with negative straight flange. So this type will include the straight flange of the hemispherical head, and inshallah we will discuss that with the pressure vessel team, because this type not usually used in storage tanks. Here for another type, which is shell from different pieces. This type of shell gives you the ability to make a shell from different blades, and you have the ability to control each blade length. Okay, now, for example, let's make this shell from 8 meters diameter, and with here the height, let's change it to 1.5 meters. And from the setting tab, let's open the calculator of that one, and here that will be the neutral diameter that we will use it to calculate the the length of this can, the circumference length of this can, and let's define the angle. Here the length, the total circumference is around 25 meters, 0.17. Okay, so that's the total length. So when we divide that value, let's say 26, divided by the available length of the delivered blade dimension, now at least you will need 5 blades. You will need at least 5 blades to make the total circumference of this shell. So let's close this and close this form. And from here, let's define the thickness to be 10 millimeters. And here, let's make this shell from 5 pieces, 5 segments. And now you will get the ability to define each blade length. By clicking on Update Grid, automatically SEG will update this grid to make it includes 5 parts. And from here, from the length tab, if we take a print screen and come here, you will find inside this list here the arrangement of the part. So that's the first part. Here you will find the length of this part, so you can define the length of the first blade on shell. Okay, and here's the start angle of this one. Depending on the length, okay, and the start angle, so depending on those, you will get the next one, which is the end angle, and you can get the same for the mid angle. Okay, so by using the information of the length and start angle, automatically SEG will calculate the end angle and mid angle. And you can figure that the end angle here will be the start angle of the next element. That's for each element here. The end angle will be the start angle for the next element, like that. Okay. And here you can figure that the end angle for the last piece should be the same with the start angle of the first piece. Okay, so here from this table, you have the ability to control, let's control this value and each blade length for that. But the last one, it will be calculated automatically based on the lenses that you defined it here. Now, let's define the first piece to make it 3 meters, 0.5, and the second piece with 5 meters, And here, let's make this one as 2 meters only. Okay. And now when you make a submission for those, I think you will need to add another blade. So let's minimize this one as 4 millimeters. When you click on update grid, automatically SEG will inform you that the deliver blade dimensions will not be enough after adding 5 segments, because the last one, if you take a look here, so if we open another image here, we take a close look here, you will find that after modifying the dimensions for those parts, the summation of those parts will not cover the total circumference. And the last piece will be more than the available blade dimensions, because the available blade is 6 meters, okay? But that one is 10 meters, 0.6. That means you will need to add another segment. Okay, so let's come back here and add the one more segment, which is, so they will be 6 segments. And now when you click on update, automatically you will get the last piece length here, calculated automatically based on the previous elements. When you change the longitudinal welding line orientation for the first part, for example, if you make it at 0, now when you click update grid, automatically you can figure that the angles here calculated based on the start angle and the each arc or each shell length. Now let's save this and click on save. When you click start assembly, you can figure that you can make shell blade, okay, from segments. Now we have 6 segments for this shell, and we already defined each blade length. So from here, the first one is 350. So let's check that. From this tree, if you open the assembly of this can, that's the first part. So from here, we take an image on that, and to this inventor tree here, that's the assembly of the can. Inside this assembly, you will find the parts here. Let's as you can see, you have 6 parts. So let's open the first part from here. Let's open the first part and get the sheet metal development of this part. And from inspect tab, let's measure the length. From here, you can figure that it's 3 meters, 0.5. It's the same defined length here. Okay, let's check the second part, for example. So let's open the second part. So from 3, let's open part number 2 and get the flat pattern of this part. And let's inspect the length of this one. You can figure that it's 5 meters. So from here, it's 5 meters. Now let's close this. And let's check another type of shells. But here you can figure that how much time you will save when you are using SEG software. Because if you try to make those parts manually and give them each part, you will give it a description and define the dimensions of each part, create a sketch for this part, and feature it by using the extrude features or sheet metal features. So you can imagine how much time you will spend to make that. But here, with a one click and some data entry, you will generate the 3D model and accurate parts for each element you will generate it in SEG software. Okay, now let's go to the next step, which is shell from different pieces. Okay, so let's reset this model. So from here, from edit, let's reset inventor model and come back to this shell. And in that case, let's select shell from different pieces and slope at bottom. This type usually used for the storage tanks with a tilted bottom. Here, if we open this, let's create a new image. And from here, for example, if you have a storage tank like this, but the bottom of this tank not a flat bottom, you have a tilted bottom for this tank, bottom like that. So in that case, you can use the first shell blades with that type. Okay, so that's the tank bottom, and here that's the first level of the tank, and here the longitudinal welding lines, and you have another shell courses with another longitudinal welding lines like that. So this type of here, which is that type, the first one, which is located here, that piece, you can use the type of shell from different pieces and slope at bottom. Okay, so let's try this. Let's make this storage tank with the bottom of this storage tank as 8 meters, the height as 1. The thickness, let's make it millimeters, and here the slope angle 1 to 50. Okay, and the cut orientation, let's make it on 90 degrees. Okay, and from here, let's change the number of segments to 5 and click on update to get the dimensions here. So let's change this one a little bit. Let's make it 450 and change the longitudinal welding line orientation at 0, for example, and update this. So we discuss those the information here and that image. So we discuss the information here. So any update on lens and click on update grid, you will update the orientation of longitudinal welding line angles and the last piece lens. Okay, now let's click on save. And before that, let's make this storage tank as a vertical vessel, or as a tank vertical for start from bottom to top. And let's click on save. Okay, and now when you click the start assembly, okay, SEG will start creating the elements of this tank. And will assemble it to the final assembly of the tank. And I will show you the changes after creating this part on a drawing, and show you that the tilt angle appear here. If you take a look here, I think it's a little bit clear. Here, if we make a drawing, quick drawing, and add a view from the back view. So let's take a look from the back view and increase the scale up to 125, for example. Actually, you can figure that the height in this side, 90 degrees, is different from the height at that side. So the bottom here is tilted. So you can use this type of shell in case if you have a tilted bottom at a vertical tank. Now let's increase the tilted angle a little bit to make it more clear. So if you change this value to 1 to 25 and click on save, now when you click start, the tilting angle will be changed on each item. Okay, as you can see here, the height at that side is changed based on the change on tilting angle at for this shell course. Okay. That's one of the available types of shell from different pieces and sloped at bottom. Okay, let's take another type, which is will give you more options to control or make another type of shells, which is shell from different pieces and thicknesses. Now let's reset the inventor model. And here let's select shell from different pieces and thicknesses. Okay, this option or this type of shell will give you the ability to control the length of each plate and control the thickness of each plate. Not only the length, but also the thickness. Okay, so from here, let's change the size to 8 millimeters, the height 150, the thickness keep it 10 and the gap 0, and here the number of segments, let's make it 5, and from here let's click on update grid, and from here you can figure that if we take a print screen and let's create a new image. We take a zoom from here. Okay, you can figure that here automatically the first lens will be like that, and the last one will be calculated. But one more option here, which is the thickness. So in that the column, you can figure that you can define a separate thickness for each blade. Okay, and automatically based on that, the start and end angle will be calculated. Now let's fix that by selecting. Let's make this one as 3 meters 0.5 and that one as 4 meters. Change the thickness for the first one to be 20 millimeters. This one will be 10. That one will be 35, for example, and that one will be 10. And the last one will be 150, and change the start angle to be at 0. And now let's click on Update Grid. You can figure that the last piece length need to be, you will need to add one more piece because the last one blade length become more than 6 meters. So let's make a new image to show you that one. Here you can figure that because we have 400 millimeters instead of 4,000, so the available length here is 600 millimeters, 6,000 millimeters. So the length of the last piece is greater than that value. So we need to increase this value or add another segment. So let's increase the value of this piece. So let's make it like that and recalculate the required values. So the last piece will be like that. Now let's click on Save. And now when you try to create the 3D model of this one, you will get a shell from different thicknesses. Yes, that's the first blade, second blade, and the blades with different thicknesses, you can figure that they will get a different color from the original blade. Okay, here to calculate it in a correct way, for that's the only type needs this process. Here, if we take a near look, you can figure that you have a little gap here. Okay, to update this part, we need to come back again to this part and make update, because in that case, SEG makes some calculation again after creating the 3D model to update that, because the neutral line which we discuss it here differs from one blade to another because they have different thicknesses. For the first calculation, SEG makes the calculation with that neutral, with that thickness as a neutral to calculate the neutral length. But after creating the 3D model, SEG will detect some information from Autodesk Inventor, and by that way, we can get the correct values and create correct angles. That's only in that type only of shell, which is shell from different pieces and thicknesses. Now, after updating and click on Save, when you click Start Assembly, the update will take place and those gaps will disappear. After calculating the actual neutral diameter for each plate with the different thickness, as you can see, no clearances here between that one and that one, like that. As you can see here, you have this shell from different thicknesses that give you the ability to, if you have, let's say, a clean outdoor with a different back plate here, so you can use this type of shell to add a clean outdoor. Here you will find another column. It's available on a shell from different pieces and shell from different pieces and thicknesses, which is mid-angle. So this column will give you an indication about the mid-angle of this plate. So you can use it to add a clean outdoor. Okay, so you can use this value or near this value to add the clean outdoor at the middle of this shell plate. Okay. Here we discuss the most common types of shell for which suits the storage tanks and pressure vessels. And here some other types for the pipe with a threaded end, or start end, or from two sides, like what we discussed on the samples that we make a connection pipe to the coupling. So the coupling has a thread at the end. So you will need to make a pipe with the thread at start or end. So you can use those types of pipes with the thread at start, end, or from two sides. Here another, the last one, which is connection point as a pipe and the connection point as a shell. And those we discussed them during the that session to make an unreal element, to use it to add elements to skirt, for example, or for a nozzle. Okay, any questions regarding this part? And inshallah, tomorrow we will make a sample and discuss the options of the annular plates, bottom plates, and here we discuss the shell plates, and we will inshallah discuss the ability of adding anchorage chair in case of using a tilted vessel, which a tilted tank, which we discussed it from it's ago, this type of tank with a tilted bottom, and how to add anchor chairs around this tilted bottom. So we will discuss the available types of anchor chairs, annular plates, bottom plates, how to make a roof with a different type of roofs, like segmental or which radial type, or arranged plates, or aluminum dome roof. How to add or change the type of the compression ring, how to add spiral stairs, clean outdoors, and manways. After that, we will discuss the options of the drawings and how we can export the bill of material. Now, any questions? We have an open discussion before ending this session, inshallah. Any questions?
Mr. Ahmed, I have just one point. Like during the training, I understood that there is some constraint that you have, that to add a nozzle on, like for example, you had started with adding a nozzle on the skirt. So for that, you had added a connection point.
Yes.
Okay, and it was like an imaginary part, and then you added a nozzle.
Yes.
So I mean, when we went through, I understood that this is the only method that you have to add a nozzle, rather than adding directly to the. I mean, the question was like, why not the nozzle was directly added to the skirt instead of adding a imaginary part?
Yes, because we have here in SEG a concept of main parts and the childs. So the childs, you have not an option to add another child to it, because the definition of this child differs from child to another. So here the concept itself not the same. So you may need to add an imaginary part to use it as a reference part, and you can make it with the same information of the child. Like if you have, as we discussed, if you have a skirt, you may need to define the imaginary part with the same information of the shell or the blade of the skirt. So by defining the inside diameter and the thickness of the skirt, if you have a nozzle and you have a connection point at the end, you may need to define this imaginary part with the same information of the nozzle, like the pipe size and pipe schedule. Okay, so the concept itself between parent and the child is completely different. Okay.
Okay.
So using the technique of adding an imaginary part.
Okay, so this is like a mandatory way that that enables us to add the parts like as a child.
Yes, but if you would like to add a part to a shell or head or cone, you can do that easily by selecting the head. After that, add the attachment. But in case if you would like to add a child to another child, like nozzle to connect it to another nozzle, or nozzle connected to a skirt, or opening connected to a skirt, so in that case you have a child.
Okay.
You need it. You need to make it as a parent. In that case, you will need to make a shift by using an imaginary part.
Okay. Okay. Got it, Mr.
Okay. Thank you. Any other questions?
From my side, no.
Okay. So here in this session, we discuss some important points regarding creating the main structure of the vessel, how to move from point to another, to flip the direction, how to make a shift for the points, as we discussed here. For example, if we let's open some samples to show you. If we take a look to this sample, for example, here, as we discussed, you can figure that it's one model, but not a separate vessels. Inside this model, we the location of assembly. After getting to the end of this one, we make a shift and flip the direction to change the direction of the assembly. So by using this technique, you can move in space to create your assembly. The same here for example, if we open this vessel, let's come up a little bit here. Okay, for this vessel, for example, you can make like that one. So you can make a vessel by using those headers. You can separate them as a separate vessel inside the same project, or you can use the technique of shift, gap, and flip to make those headers by that way. Okay, and here, so we are discussing the options to make that, and here we discuss the option if you have a nozzle case, not from pipe or from blade or a forged hub, it's an elbow or a reducer or a duct. You may have a need to connect a rectangular duct directly to the shell. So how to make that? Because the nozzles is not include this type of duct. So in that case, you may need to make an imaginary part as a nozzle. At the end of this nozzle, you will connect the duct to get this configuration for like this elbow or this cone. So this session is very important to add the base or make the base to use SEG software before going to the next step, which is creating an equipment. Okay, any questions? Hello?
Not from my side.
Okay. Is there any questions on the chat? Okay. Can you please explain 2 of 3 different size nozzles on dish of different orientation? What does that means? Explain 2 or 3 different size nozzles on dish. Okay. Let's reset this model. So from here, let's reset this model and create a bottom head. So let's select this vessel, and from elements, let's add bottom head. And for this one, let's make it with 2 meters diameter, for example, 20 millimeters, 100 millimeters. And let's add the first nozzle. So from here, let's add a nozzle with external projection as 1. And that nozzle, we during this session, we make a nozzle from pipe. Now let's try to make a nozzle from blade. And in that case, let's define the outside diameter of this nozzle, the neck, the outside diameter of the neck, the thickness, longitudinal welding line orientation, and offset from the center line. So let's define this offset to be 500 millimeters. let's add a repad, and from here let's click on save. Now let's add a flange to this nozzle. So N1 flange. Okay, and if you let's define this flange to be here, those are standard flanges, not designed flanges. So let's make this nozzle, let's say round. Let's make it long with the neck resting face, and let's make it, let's say, like that. And okay, to check something regarding the projection, and the projection we will discuss it on inshallah on the next session, which is this calculator. But okay, let's remove it and discuss it in detail. Save time to discuss it in detail on the next session. Now we have this nozzle and with that projection. Now if you click on assembly, you will get a nozzle from blade connected to the bottom head. I think the diameter of this head is not correct, so let's stop the assembly and come back to the head and define the inside diameter. Okay, so SEG goes to the next step. Okay, now let's, after finishing the assembly, because the diameter of the head is not correct, let's save this and files. Now let's reset the inventor model, and let's create this nozzle. After that, let's add a long weld neck nozzle and a forged nozzle with as a hub nozzle, and a nozzle with reinforced lips to check the different options of nozzles on the bottom head. Inshallah, in detail, that will be discussed on the pressure vessel sessions. Here we have this nozzle as a blade from blade, and you can figure that you have a longitudinal welding line. So if you open this nozzle and open this part, which is this shell part, when you create sheet metal development, you will get this contour of the nozzle connected to shell. Let's close this for the assembly and come back here. Now let's add another nozzle as a long weld neck nozzle. So from here, let's add another nozzle, which is N2, and make it from here. Let's select it as a long weld neck nozzle connected to shell. Change the rating of this nozzle, change the size, and define the location. Let's make it 600, and change the orientation to make it on 90 degree. Keep the projection as it is and click on save. Let's add another nozzle, which is N3. And this nozzle, let's make it as a forged hub nozzle. So from here, let's select a standard forged hub connected to shell. So in that case, you will be able to define hub height, hub thickness. So from here, let's select it as in inches. Select the scalable at the end of this pipe. Define the offset and the orientation. Let's make it 180 degrees. Keep the hub thickness, hub bevel height. So all of that, let's keep it as it is. And let's add another nozzle as N4 and make it nozzle with a reinforcement and self-reinforcement forged hub. So from here, let's select self-reinforcement forged hub. So you have a lip here at the end of this one. From here, let's select the size, select scalable of this nozzle. This will define the offset from the center line and the orientation to 170, and the projection, let's make it 300. Hub information, hub height, hub thickness, all of that. And here the thickness of the this lip. So here the head thickness is 20, so we can increase this thickness to 30, for example, or make it equal. And here, if you would like to make it, that's the value of bottom pellet. And if you would like to add a chamfer here, so the chamfer value will be 1, 2, 3, so 10 millimeter, 30 millimeter. So from here, if you click on save, and now when you try to create the assembly, we will get 4 nozzles at the bottom. One of them is a nozzle from blade, and nozzle as a long weld neck nozzle as a forged hub nozzle, the last one a forged hub with lips, and the insert bed of this lip with a different thickness than the head thickness. So you can figure that you have this one, and as you can see, the thickness of the insert bed of this one is greater than the thickness of the head, with 10 millimeters difference. Okay, now you have different options to control the angle of this one. For example, if we open N1 here, you can make it parallel to the center line. Sometimes you may need to make it radial, so it will be perpendicular to the outside surface of the head. So in case of making it parallel and click on start, the center line of this nozzle will be perpendicular to the outside surface of the head. Like that. And if you would like to control this angle, you have the ability to do that if you, in case of making it tilted. So with 90 degree, it will be vertically. But if you would like to control this value, like make it, let's say 80 degrees, and let's increase this projection a little bit, and click save. So the contact angle here between the vertical line and the center line of the vessel will be 90 degrees. Here, so if you make a center line here, if we open drawing like that, and if you open add this vessel to this drawing, let's make it on a vertical position like that. Okay, increase the scale a little bit. Let's make it 1 to 10. And here, if you add longitudinal welding line here to define the center of this nozzle, if you extend this nozzle here, so that's that 20 degrees. So you can control the orientation of this one. For example, if you would like to that and click on save, now when you click start assembly, and inshallah that we will discuss it during the pressure vessel session. Inshallah. Now, if you try to open the drawing, you can figure that the orientation of this one is completely changed to 120. Any other questions? Can we can we show shell plate bevel size or degree? What do you mean by show bevel size or degree? I don't understand what bevel size. Anyone can clear this point to me? Hello? Hello? Hello?
Hello.
Aywa. Hello.
Yeah, this one he's asking the bevel size of the weld. Like we are welding the shell plate. So how to show the bevel size? Anything we have to show in the detail, or it will be in the 2D drawing?
I don't understand what do you mean by bevel size. You mean a
Because
chamfer
when
at the
we
end?
When we connecting the two shell courses, there will be a
Okay.
bevel, like a 30-degree
Okay.
beveling
Okay.
for
The
connecting the
chamfer
two
at the
shell
end.
courses.
Okay. Okay. Or here, for example, if you have this one, that you have this head, you can make a chamfer, and by using the chamfer options, you can make this chamfer if you would like to repair it, and it will be already included inside the drawing. You can make a weld detail in your drawings. Like for example, let's look at this one. You will include a detailed drawing for that to indicate the chamfer values and for the longitudinal welding lines or circumference welding lines. So if you would like to include it on the 3D model, you can make it by an easy way, like selecting this face and define the edges that you would like to make a chamfer on it. After that, define the value. Let's make it 19 and make the angle not 45, let's make it 30 only, or 50. It's up to you,
Okay.
up to your fabrication capabilities in your workshop. So after that, you can make a chamfer. So now you have this head with a chamfer end. The same thing, you can do it with the shell. That's in case if you would like to include that in the 3D model. Okay. But if not,
Okay.
either way, you have the detail already will be indicates that in the drawing. So any longitudinal welding line will be according to this detail. Any circumference welding line according to this detail. Any flange to nozzle will be like that. You know.
Okay, okay, we understand that. Which means in the 2D drawing we can show as a typical well detail. No need to
Yes.
show in the 3D model. Okay.
The 3D model, okay, because a lot of orders will increase the size of the part, and that will increase the number of lines inside your drawings. Okay, and that will take a memory, not a huge memory, but I'm talking about you sometimes decide that it's not important in my drawing, so no need to spend the time to create it.
Okay.
Any other questions?
Yeah, and this shell long seam orientation we can fix in the 3D model.
Again, please.
Yeah, suppose we have number of shell courses, shell 1, 2, 3, 4. So each shell course, the long seam weld joint having different orientation. So how we can fix it that one in the 3D model? In SEG, any option is there for selecting the long seam for each shell course?
Okay, now let's add two shell courses here to show you this point. Let's add one. And from here, let's select the shell type, define the inside diameter, the thickness, keep the length, and keep the orientation of the longitudinal welding line as it is. And now let's add another can, which is can 2. Make it looks like can 1 and click on save. Now when you create this part, you can figure that, sorry, the height, I make it 150 only, not 1,500, no problem. We can increase it after creating. Now let's come back here and let's reset the inventor model. Let's delete this head. Okay, and let's come back here and modify the setting. Let's increase this one like that and modify the height of this shell. Add another can. Now, when we try to create this, you will get 3 shell courses with the same longitudinal welding line orientation. And here, if you would like to change the longitudinal welding line orientation, it's a text box inside each shell of those. So you will select the node from the tree and redefine the orientation of the welding line. For example, here, the first course longitudinal welding line orientation is at 45 degrees. So here, the longitudinal welding line orientation, you can change the orientation of this one to 0 degree. When you click Save and click Start, automatically it will be reflected to the 3D model. And you can figure that the location of the longitudinal welding line changed. For the second shell, for example, here it's 45 degrees. So if you change it to 20 degrees and click on Save and click on Start Assembly, you will change the orientation of this line. Now, let's use another option to, if you would like to, for storage tanks, if you would like to make an offset from here to there with a defined angle like 2 meters or 3 meters. By using this calculator here, you can do that. For example, here for this vessel, it's that's the neutral diameter, and from here, let's make this offset with 3 meters, for example. When you click on calculate, that's the angle longitudinal welding line orientation, which gives you the arc offset from the end with that value. So we can take this value as a copy and you can add it here. So for the second one, you can add the longitudinal welding line orientation at this degree. When you click Start Assembly, the longitudinal welding line orientation of this one here will be offset here. That line will be offset from the first line here with 3 meters offset. Okay, so by using the calculator, you can do that. I hope now I answered your question, or still you have any.
But if one single shell core is having two weld seam, means that it is made from two plates. So can we make two long seam?
Okay, okay, no problem. We did that during the session. We add a different shell blades with different thicknesses. All of that we already created. But no problem. Let's repeat it again here. If we have this shell plate, let's increase this the diameter of this one to 8 meters and click on Save. And that one, let's make it shell from different pieces like that. So let's take it from different pieces, increase inside diameter, and here let's calculate the required number of plates, 50 millimeters, and click on Update. Increase the length of this one, and let's make it 4 segments. Okay, let's decrease this one 5 meters and update this one. Let's click on Save. Now, when you click on Start Assembly, that's the first course, including 3 blades. And the second one, we defined it as a shell from different pieces, and we defined each blade length. After creating it and assemble it to the final assembly of the equipment, you will get that you have a different longitudinal welding lines orientation. And here for this form, when you select that, you can figure that the start angle for the first longitudinal welding line, it will be here, and the second element, that's the first start angle, longitudinal welding line angle. And this value will not be editable because you have a length here and the start angle, as we discussed here. Because by using the start angle and that length, you will get the end angle here, which is the start angle of the next part. And that angle will be, by using that angle and the length and orientation. And easily from the 3D model, by making a visual inspection, you can detect if you have any clashes with the welding lines or not. Anytime you would like to change the welding line orientations, you can change it in that type. For example, you can change it from here. For that type of shell, you can change the start angle of the first one, and automatically it will be reflected to the other. So for example, let's make it at 0 degree and update this grid, so you can figure that the angles will be changed. Now when you click start assembly, you can figure that you will get a clash between some vertical longitudinal welding lines, because we give them the same orientation. At the bottom shell, we make it at 0, and in the top shell, we make it at 0. If you take a look from the front, you can figure that you have the same longitudinal welding line orientation at this part. Okay, I hope now your question is covered.
Yes, this is clear.
Okay. Any other questions?
And one more thing, when we are inserting a nozzle to the shell or head, how about the weld detail between the shell to nozzle joint? Is this predetermined in the SEG, or after inserting the nozzle, we have to make the weld detail in 2D drawing separately?
Okay. Okay, for that, let's try something here. If we have a nozzle with internal and external projection, let's add in one. And from here, during importing this nozzle, let's make it as a nozzle from pipe, 24 inches pipe with a rebad. Here, if you try to add a rebad, after clicking on save, let's give it a random values. But from here, if you open a set weld, you have a set weld detail for the nozzle. So from here, you will get a button for set weld. From here, you will get the ability to change the chamfer if it's a single V or a double V. So you can figure that the image here will change based on the selection of chamfer, single or double. And here you can add no clad or parent clad, or nozzle and the parent include a clad. So from here you can define the fillet weld values. So for here dimension A, which is the weld between the neck and the rebad. Okay, dimension B, between the rebad and the shell, or the parent if it's head. And C is the fillet weld from inside between nozzle and parent. And by the way, during creating your drawings, you will get an option to select the welding details, which will appear in your drawing by automatic. So you can include the welding details inside the drawing. Any other questions?
So if we enter this weld detail here, after inserting the 3D model into 2D drawing, this weld detail will automatically come to the 2D section also, whatever we enter?
No, you decide what detail will appear in your drawing. In your drawings, you will, from the weld library, you will decide which welding detail you need to make it appear inside the drawing. So it's up to you. So you will select the required welding details.
Okay, so my question is, suppose when we create one nozzle here, we are adding some set welding detail here. Okay.
Yes.
So
this weld, okay. So this weld detail, when you defined it, for example, make this one 10, 22, 6, and click save. On the nozzle table here, if you open the nozzle table, you will find that nozzle will be defined here as nozzle N1, and that's the surface. And if you take a look to the those columns here, let's make it print screen, and here, and if you take a look at this area, yes, that area here, you will find here that's the weld style, which defining the style of the weld of this nozzle. And here the fillet weld at A, K, B, and C, which defined it here on the you defined it here on this form, which is set weld. And here the style of welding is NW7A, which appears here on the nozzle weld style, which is that one. Sorry. Okay, because you will select a detail from the weld library to make it appear on the drawing, like NW 7A. So those dimensions, which is A, B, C, will be referred to this detail. Okay.
Okay. Okay. Okay.
Okay. One more question here. If the pressure vessel team attend this session, or I will need to repeat the first part of the equipment or the basics of SEG again. Did they attend this session?
Yeah. All pressure vessel team already there attending now.
Okay. Okay.
So tomorrow's section will be the tank or tanks?
Yes, will be 4 tanks only.
Okay. So tomorrow you will be showing one sample tank from your library, or we have to provide any drawing?
We will discuss the features of bottom annular plates, the anchor chairs. Today we discuss the shell types. We'll discuss tomorrow, inshallah, the roof options, roof structure, the simple roof structure, how to add a ladder and a spiral stair, how to add the nozzles, a clean outdoor manway. Inshallah, that we will discuss it tomorrow. After that, we will proceed with the drawings, how to prepare the bill of material. And on the last session of Autodesk Inventor session, we discuss how to make your own border and the title block. So we will not need to repeat the same thing again. You can revise this session, and we will directly complete without repeating this step, which is creating the border and the title block. After that, we will add the dimensions for the tank, add the balloons, and how we can reflect the balloon number to the drawing and make it looks like the same item number in bill of material, inshallah.
So pressure vessel, can we give one sample GA drawing to you so that during the pressure vessel training, can you use that reference drawing?
Again, please.
For the pressure vessel training session, before that, we will give one sample GA drawing to you, which is our existing pressure vessel in our shop.
Okay,
so
no problem.
It will be better for us to understand.
Okay, kindly share it today to study it before the training.
Yeah.
Give me enough time to study it.
Yeah, I will give you.
You should give me enough time to study the drawing first. Don't send it on the same day morning. I will not be able to study the drawing and get out the dimensions of this.
Okay, I will send to you after this meeting.
Inshallah. And by the way, would you mind to send me the evaluation form for the Autodesk Inventor training from your side? I send you the evaluation form from 2 days ago. I think Fawzan shared it with your team. So kindly send it back after adding your comments.
Okay.
Did you receive it or not?
We will check. We will check the email. Otherwise, you can resend it after this meeting.
Okay, I will ask Fawzan to send it again to you. Sure. Any other questions? Or we close this session, because Mr. Misbah tell me that he will need to close this session at 11:13.
Yeah, I think we can close. There is no other question.
Okay. Thank you so much for your valuable time.
Okay. Thank you.
Okay.
Thank
Have
you.
a nice day. Assalamu alaikum.